So to say again for the recording, because I just started the recording, today we're going to be talking about two things. One of them is going to be how to avoid magic numbers in your programming, which magic numbers, I'll explain briefly later, are constants or sort of arbitrary values that you introduce that make your program somewhat fragile when you want to reuse the code. And then the second point is going to be on using things like predict for the linear probability model and how to interpret coefficients in both the linear probability model and the logistic regression. So this lecture should probably only take about an hour, like normal for the first Thursdays in a chunk. And it'll primarily be oriented around code. So most of it will be done sharing my RStudio screen, if that's okay. So if there are no other questions before we start, I'd like to get going. Okay, so I have this notebook up, which is the notebook on workbook 1. Oh shoot, I need to close these because those are confidential. So I have the notebook up on long waits, workbook 1 kind of stuff, and I'm working with the times data here. So something that I see occasionally in your code, which probably is driven from you copying and pasting things from me, which I guess I should probably model better practices if I'm going to do better. But generally speaking, a magic number in programming is when you use kind of like a constant or some kind of non-data dependent value that you use to structure your program. So what do I mean by a sort of a data dependent value? Well, in the times data, let's say, I have some pubs that are, sometimes that refer to waiting times at the Berkeley, sometimes that refer to waiting times at the Gallimalfrey, and sometimes that refer to waiting times at the Milk Thistle. And I've suggested that you use, let's say, a filter operation to select rows. Oh, the library tidyverse. So I've suggested that you use filter operations to select rows. And I've also selected that suggested that you used select operations to select columns. So the alternative to using these kinds of functions is to use direct indexing. And this is the kind of indexing, sometimes in some corners it's also known as slicing. You've seen this before in your course because this is how we taught you initially to select columns. So you might do something like times, and you might say waiting and pub to get those two columns. Now, this selection of columns based on their names is about the same as the use of select to select on names. They're basically the same thing. The reason why they're both considered okay, or they're both kind of functionally equivalent, is because you're using the names of the columns, which are constant regardless of whether or not the data frame is changed or processed. So the assumption is that the waiting variable is going to remain the waiting variable until it changes form, until it's either summarized in a group by or mutated. So if you think about that, the name of a variable is generally going to be constant across transformations until it is what's called mutated. So that's where that mutate function name comes from, is that when you're working with data, the variable names should probably stay the same up until you kind of mutate the data and change its structure. So either that's a transformation like a group by, or it's changing the name of a column or something like that. So selecting columns based on their name is fine, and it's okay to do that using the select verb in the tidyverse. Now, what I don't want to see you do is something like this. In that case, you're selecting columns based on position. And this, again, is kind of a useful way that people work with data frames, but it can be problematic because once columns are inserted or removed, the indices change. So inside of a single kind of tidy chain of pipes, you can drop columns and add columns, which then changes the reference of the first and second column. So if you use position to identify columns, that's considered to be a sort of fragile approach to selecting data. If you use names, by selecting the individual kind of columns by name of what you want, it's considered to be more robust. And these actual indices, 1 and 2, are something that are sometimes called a magic number. In programming, a magic number is a data-dependent number that you use to process your data. Okay? A very clear example of that is using the column numbers as I've just shown you here. If you use 1 and 2, and then I add a column to the left, 1 and 2 no longer refer to waiting in pub. However, if I always refer to waiting in pub, I'll get those columns no matter if I add a column or remove a column from the data frame. Does that make sense to folks? Does everybody see why you might want to avoid those kinds of what they call magic numbers? So the other kind of obvious way that this becomes important then is when we talk about the filter. So if I want to filter just for the pubs that are in the Berkeley, then I can do something like this. And other people maybe use the construct that they're more familiar with, which would be something like times $pub is equal to the Berkeley. And this is basically the other filter operation. And if you look carefully, it's actually somewhat less typing. It's more compact, and that's okay. I would prefer that you use the tidy verbs that I've taught you, but it's okay also to use this kind of what they call slicing syntax based on the Boolean variable. And you also know about subset times pub is equal to the Berkeley. So you know both of those operations. That one, and of course the one that I've taught you now, which is the tidy form using the filter function. However, some of you did something like this. Grab me the first 6 rows of the data frame. In this instance, that range of values is data dependent. If I change the sort order and grab the first 6 rows, it's not going to be the right rows. However, if I use filter, wait, I was working with the Berkeley before, wasn't I? I'll get the right values. They'll be in a different order, but I'll still get what I intend to get. So my point here is that if you're ever finding yourself slicing or dicing a data frame based on indices, you're probably not using the tidy tools that I've taught you. The tidyverse and all of these kinds of tidy data transformations try very, very hard to avoid these kinds of magic numbers. Okay? So one way you can think about this is, will my operation work if I've shuffled the data frame? If it does, then you can probably say that your solution avoids magic numbers. You can probably say that my solution does not have any kind of data-dependent indices. I'm only using variable names, which exist in the same way if I rearrange the columns or insert columns or remove columns. And likewise, if I'm using filter operations or subset operations, then they'll give me the right result regardless of if my data frame is sorted or rearranged. Magic number you can think of is a configuration, a slice index, 1 to 6, that if I change the structure of my data frame without changing the information content, this operation will give me the wrong result. So you want to use things that are robust to those kinds of changes because they happen a lot, and you don't always have a good idea of when they happen. So basically, try and avoid using direct indexing with integer values, and you'll be fine. Most of you didn't do this. Most of you did, use the tidy tools that I taught, and you did okay. So no big worries there, but I just wanted to tell you a little bit about this so that I can make it clear. Are there any questions on this kind of magic value issue that I'm talking about and how you can use sort of data independent indexing and selection? Okay, seeing none, then let's move on. Okay, so this kind of prediction problem for the workbook 1, I've talked to you a little bit about how when you look at the times data and you fit a linear model to try and predict the waiting time for each individual pub, that if I just fit a linear model that's predicting waiting based on the pub you're in, I get back the mean waiting time. Oh, Georgia has a question. Yep, I'll get there. So in the last kind of practical, I talked a little bit about how most of these, what are called conditional expectations that we're making for our y's, are based around the means for our individual groups, right? And that if I have a continuous x, I need to make expectations about alpha plus x beta. So I need to be describing the distribution of responses, y, at a particular level of x. So regression is all about conditional expectation. What value is y going to take if I observe x? And in the simplest example, our guess for that is the average y at some x value. So here, our best guess for the waiting time in a pub, you can think of this as your y, and you can think of this as your x, is that you have a 4.7 minute wait when x is equal to the Berkeley, and that's just the average of waiting times in the Berkeley. Sophie asked, what does the 0 mean? The 0 means do not fit an intercept. Remember, in the last practical, when you just used pub, it fits a contrast, where the effect of, say, being in the Gallimaufry is equal to intercept plus the Gallimaufry. Whereas if I use the 0, or I do pub minus 1, it's the same in both cases. I fit a model without an intercept. Okay? So again, this is conditional expectation. In language, I write that E, Y given X. So you should have seen this in the workbook, and it's about building a guess for Y when X takes on a particular value. Okay? Now, the times data is very interesting. As Georgia has noted, your friend is not very consistent about when they think a wait is long. As I argue in the notebook, some of the waits that are considered long are longer than some of the waits that are considered short. For instance, looking in the Gallimaufry, your friend waited, 0.6 of a minute, and they thought that wait was too long. Then your friend waited 0.8 of a minute, and they thought that wait wasn't too long. So there's some inherent randomness in how your friend is making the decisions about what is too long or too short of a wait. Does that make sense to everybody? There's a little bit of sort of randomness in how your friend is deciding how long the wait is. But it's still the case that some waits are long and some waits are short. Does that make sense? If you read the workbook, you'll see kind of a rationale for what's going on here. So your friend is not consistent in their judgment. It's not just a simple function of, oh, I've waited more than 3 minutes, that's a long wait. It's much more complicated than that. For instance, your friend has been okay with waiting up to 2 minutes 70 in the milk this drink. But nearly every wait in the Gallimaufry that's above a minute is a long wait. So why would they be willing to wait much longer in the milk thistle than they would in the Gallimaufry? Well, it's likely that there's something about the pub and also something about how long the wait is that changes your friend's perception of whether or not the wait is too long. If a pub is nice to be in and is playing good music and it's not super crowded, maybe they're okay with waiting for longer. Alternatively, if the pub's really crowded and it's very obnoxious music playing, your friend's going to want their drink quickly so they can get back to what they were doing. So what this exercise is supposed to get you to think about is how to build conditional expectations for a discrete y with both a continuous x and a discrete x. So we're going to build different predictions for different pubs given the waiting time. Hannah, yeah, definitely. So if you give me sort of convincing justifications for why you're building these kinds of expectations, that's great. It kind of demonstrates an engagement with the actual text of the workbook rather than just kind of, or the text of the assignment as well. But I'm not going to like say, oh, that's extremely implausible an explanation or anything. So I'm not looking for you to do original research to justify the claims. I'm just sort of asking for you to engage with the kind of practical implications there. So what I meant to show by this table up top, where I'm showing you whether or not a wait was long based on the wait time, is what I was just talking about before, right? That a pub like the Milk Thistle, the average long wait is 10 minutes. And the average wait that's not too long is 2 minutes. But in the Gallimaufry, the average long wait is less than 2 minutes. So if your friend had a consistent judgment, they would judge most of these things as maybe not too long, or they would grade all of the waits in the Milk Thistle as too long. So it's not just a simple cutoff based on how long your friend's waiting. It depends on where your friend's waiting. Okay? So if you, again, read through the workbook, you'll kind of see where I'm coming from with this. So going down, I have this sort of, I think, let me see the, yeah, no, this is okay. So if we were going to fit a linear probability model on this long wait variable, I've told you that it's just the same as a linear regression on a binary outcome. This means that you can just use the same code as you know before to run the linear regression. So to do that, you can run a linear model on the binary outcome, which is long wait, and that's a function of what pub you're in plus how long you wait. And since I'm asking you to fit a model with separate intercepts for each group, I'd like you to fit it with a +0 or a -1, however you're more comfortable thinking about it. But basically, I don't want you to fit a separate intercept. I want you to fit every category having its own intercept. Okay? And last week we talked about this as a fixed effect model. For each pub, it gets its own intercept. But the effect of weighting in that pub is going to be constant over all pubs. So if I run this regression, this is the linear probability model automatically. That's because the binary outcome is your y, and all these other things don't necessarily matter. The thing that makes it the linear probability model is that you're regressing onto the binary outcome, y. Okay? So how you read this is that if you had a waiting time of 0 minutes, your friend would have a 49% chance of saying the wait was too long in the Berkeley, a 61% chance of saying the waiting time was too long in the Gallimaufry, but only a 5% chance of saying the wait was too long if they were in the milk thistle. Does that make sense to everybody? You read these things as the baseline when this is equal to 0 for y. And since y is binary in this case, these are the probabilities that whatever your y variable is equal to 1. So in this case, this is the probability, given everything else is 0, that y is 1. The waiting time effect, because waiting is a continuous variable, is the increase in probability per unit increase in x. So for every additional minute that the probability that the wait is going to be too long increases by 0.07. So every minute you have an extra 7% chance that that the wait is going to be too long. Does that make sense to everybody? It's the same exact kind of interpretation we had before, where the pub effects are like the unique baseline or unique intercept, and a continuous variate, it's a unit change in x results in that change in y. Noah, yes, the weighting effect is across all pubs. We haven't changed that depending on pub yet. And we probably won't do that till next. So as I show then later in the workbook, this corresponds to 3 different lines. So the y-axis in this plot, let me make this a little larger. The y-axis in this plot is the probability that a wait is too long. And the x-axis is, Hannah asks, so the coefficients are baselines, but don't give an indication about what happens with 1 unit increase in wait for each pub. Exactly right, Hannah. The coefficients for each pub are like the intercept. So the intercept for the Berkeley is where that red line hits 0. The intercept for the Gallimaufry is where that green line hits 0. The intercept for the milk thistle is where the blue line hits 0. Just like before, just like in a linear regression. But now, since we have a binary outcome, these represent probabilities. That's all. Yes, exactly right, Noah. If someone got a drink in the Berkeley without a single wait immediately, it would be a 50% chance that they thought it was too long. If your friend is served in the Gallimaufry immediately, it's a 60% chance that it's too long. Yeah, your friend's really impatient. Yep, exactly. So that's what this linear probability model is telling you. It's the same thing as before, except y is binary. And because y is binary, you now read these things as probabilities. That's it. That's the only difference here. These are still the effect of being in each pub, and this is still your waiting time. Now, we could mean center that in a lot of really fancy ways, but I figure it's helpful right now just to think of this as your baseline over here. And likewise, if I remove this 0, it's the same model, but now with contrasts. So you'll see, I need to move that up a little bit. You'll see again, this intercept for the Berkeley is the intercept here. And you get 61 by adding 11 to 49. So this effect in the contrast model is equal to the intercept plus the extra effect of going to the Gallimaufry. And likewise, the effect for the milk thistle in the contrast model is equal to this effect when you do the intercept plus that distinctive one. Does that make sense how these two models are related? This is the contrast model where we're saying the Berkeley is our reference category. And this is the fixed effect model where we're just fitting separate intercepts for each group. They give you the same exact lines when you actually estimate them up here. It's just this one measures the intercepts relative to the red lines intercept. And the fixed effect model up top gives you the values for each intercept independently. That's it. So I'm not going to spend much more time on that contrast model. But it suffices to say your friend is very impatient. But in our model, we only fit a single effect of waiting times as, or the effect of waiting an additional minute. So the effect of waiting an additional minute is that for every minute, your chance of it being too long of a wait increases by 7%. And that is not 7% relative to your starting probability. That's 7% each time. Okay? So it's like 7 percentage points. And this is kind of a common point of confusion here because the logistic regression we'll talk about later does not work like this. It is a relative change, not an absolute one. The linear probability model is an absolute change. So the slope of this line, the gradient of these lines, is 0.07. And that describes the unit change in the chance a wait is long when you increase the waiting time by 1. So I'm going to call this LPM for linear probability model. Now, to answer Finn's question a long time ago, if I wanted to guess whether or not a friend would have too long a wait in a pub for a particular amount of time, I can use the predict function. Using the linear probability model, I want to know what happens when my friend is in the Gallimaufry and the waiting time is, say, 5 minutes. Oh, wait, that's not right, sorry. So like before, we need to do a scenario data frame. So I want to know the scenario when my friend is in the Gallimaufry and they wait for 5 minutes. So scenario is just a data frame with 2 columns, pub and waiting, that have the values for the prediction that we want to make. In the plot, this is going to be the location of the green line at 5 minutes. So we find on the x-axis, we go to 5, and we go all the way up to where the green line would be. Okay? So if we predict with the model, LPM, in this scenario, it seems like I've just lost. Hello, can you see me now? It seemed like something happened with my screen share. Can folks see me? Hello. Yeah, okay, cool. Sorry, something happened. Great, okay, so I'm gonna proceed. So when you do this predict function, the model goes first, and then a scenario goes second, and you get an out-of-sample prediction for the scenario you've specified. So if your friend waits 5 minutes in the Gallimaufry, there's a 97% chance the wait's going to be too long. Does everybody see how that works with the predict function? I'm specifying a scenario which I want to evaluate, and then I'm using the linear probability model to assess that scenario. Now, I could change that, right? And I could say, you know, if my waiting time is 7 minutes, and I could run the prediction again. And now, I get an 111% chance that the wait is too long. As I talk in the workbook, that's against the law. You're not allowed to have percentage chances that are bigger than 1 or bigger than 100 and smaller than 0. Probabilities have to be somewhere between 0 and 100. And you can't have a 111% chance of something happening. You're not allowed. The reason why this happens is because the change in probability is linear in the linear probability model. And I know that that sounds like a tautology, but just look at the graph. If we just look at the fitted values for the existing observations in our data, our wait at the milk thistle, our longest wait, that's over 15 minutes, has a 117% chance of it being too long. You can see on this plot that refers to this prediction. So the linear probability model is not restricted to generate probabilities between 0 and 1. This means that it's mathematically ill-conditioned. It can generate predictions that are way, way, way too large. In fact, impossibly too large. So what we kind of want to do is to make it so that this line slows down when it gets to 0, and then kind of asymptotically just stays at 0 when x gets really small. And we want the same thing to happen as it approaches 1. We kind of want it to flatten out and then never go past 1. At a point, we just want it to be an extremely likely probability, an extremely, large probability close to 1. And we actually don't ever want it to cross 1. But the linear probability model can't do that. It only generates these valid predictions within the support of the data, and can sometimes even, for instance, this observation and this observation, generate invalid probabilities. So the linear probability model can be useful as a first step to just understand the probabilities involved in a problem, but it's a bad idea generally to make good predictions about probability. If you're just interested in the 0-1 classification, Exatric asks, can we not just assume that a probability of over 1 also means certainty? And likewise, can we assume that a prediction below 1 or below 0 might mean certainty of not? Yeah, you could. And that's typically done in a linear probability model. But the big issue is that a change from something being, say, 99.99% likely and just 99% likely is that those are big relative changes in the likelihood of an event. We're talking about, the difference between an asteroid striking you personally and, a bear attack or something. The difference between those two events is so extreme that using this kind of linear relationship between probabilities doesn't really capture that very well as well, especially when you get out to the tails. So there are a couple of reasons why the linear probability model, it works, and that's why I'm teaching it to you, because it's a very quick and dirty, good way to get rough estimates of probabilities. But if you're really concerned about accurate predictions of probabilities, it's not exactly the best. If you're just interested in classifications, it works okay. You just assume that everything that's negative or above 1 are the relative kind of predictions you'd make otherwise. So if you get a negative probability, you just assume that the prediction would be 0 for the class. And likewise, if you get a probability of over 1, you just treat it as, oh yeah, we're absolutely certain that that's a 1. Okay? That's called the linear probability model. And it just happens by running a linear regression on a binary variable. So the other way to proceed is to do this logistic regression. And like I did in the lecture earlier this week, and as is done in the reading, there's a bit of a step that you have to go through before you get to the logistic regression. You have to think about the binary variable having some probability, here denoted pi, and then you use the log of the odds to get to a value that we then run linear regression on. So the logistic regression is just a linear regression on this quantity, the log odds. And it's kind of confusing, but if you just think about it as a really complicated transformation of y, that's all it is. We're just transforming y into something that's a little bit easier to do a linear regression on, so we don't make invalid predictions around 0 and 1. So Hannah asks, if it's a linear regression of log odds, then how come the plot is non-linear? So this is the logistic curve. And Hannah's question is, if it's a linear regression, why is that non-linear? Well, this is where linear regression is kind of cool. I can turn many, many, many different kinds of variables into a linear space. So here we're taking the decidedly non-linear and bounded probabilities and transforming them into these log odds. When I run a linear regression in terms of the log odds and then transform that back, I then get a non-linear regression. That's the whole point of what they call generalized linear models, of which a logistic regression is one special kind. It is a linear regression, but it's not a linear regression directly on y. We do a transformation of y, run the linear regression on that transformation, and then stick them back into the original space. And I get something that's nonlinear. I'm not asking for you to be able to replicate the mathematics of that, because it's somewhat sort of challenging. But if you walk through the example that I give you in the workbook, going from y to its probability and then its odds, things should be a little bit clearer. Also, the reading has some really good explanations of why we do this transformation. But again, all I can really say is that what I said on Monday. We do this transformation so that we go from having something that's bounded and particularly ill-suited for linear regression, which is the probabilities, and we kind of want to stretch it out when we get close to 0 and close to 1. So as x continues to increase, as our probabilities get more and more and more certain, closer and closer to 1, the rate at which the probability increases gets smaller and smaller and smaller. And as I was saying earlier, this reflects the fact that changes in really, really big or really, really small probabilities are very large relative to one another, but they're not large in an absolute sense. So if the linear probability model just assumes that changes in probability are linear for every change in x, the logistic regression assumes they're linear in the log odds, not the probability. So it's a linear regression on the transformed space, but it's a nonlinear regression in terms of the probability that y is 1. These kinds of models where we transform y into some other space and then run a linear regression are called generalized linear models. And they exist for binary data, for many, many, many different types of count data. They exist for data that's constrained to be positive. They exist for all sorts of things. You do a transformation to y to get it to something that looks like a normal linear regression. You do the regression there, and then you transform everything back. And it works pretty well. If you had a plot of x against log odds, that would look linear. Yes. It's just a line centered at 0, 0. And it would be a linear, just a standard x equals y line. But it's non-linear in the log odds. Okay? So this, see, I guess the best way to think about it is going all the way down to the end, right? If I have this probability that these things are a long way, predicted by my logistic regression, these are linear in the log odds. But as you get closer and closer to these large probabilities, our predictions flatten out. And logarithms kind of make things relative. So if I have a unit increase on the log scale, it's an 100% increase on the original scale. So if I go from 1 to 2 on the log scale, that means that I might be going from 10 to 100, depending on my base, in the linear scale. So they're big. It's a way to kind of, do you remember when we were working with prices, and when we log y in terms of price, we get percentage changes in terms of beta. The log odds, x against the log odds, would just be a linear regression. But we don't actually observe the probabilities, nor do we actually observe the log odds, which is why this is kind of confusing sometimes. So I want to talk a little bit about the actual code to fit these models. So earlier, when we did our linear probability model, all we had to do was specify a linear regression. The logistic regression is, as I said before, a generalized linear model. So we use the GLM command. And our outcome in this case is still the long wait. And it's still binary. So we're still trying to predict whether or not our wait is long. Now, generalized linear models work a little bit better when you fit them in terms of a contrast than in a separable, like a fixed effect form. So here I'm actually going to use a 1 plus pub plus weighting. Then I'm going to say my data is equal to the times data. And there's one extra thing we have to tell the generalized linear model function. we have to tell it what distribution we expect y to have. So we do that using this family argument. The family tells us, okay, what distribution or family of distributions is our y variable distributed according to? And I've told you that a binary y, we usually model that as a Bernoulli distribution. And in a little bit of a frustrating pedagogical reason, R groups together Bernoulli distribution and binomial distribution together when we're using these GLMs. And it's just because the Bernoulli distribution is a special case of the binomial. So in order to run a logistic regression, you type this GLM command, you put in the same exact thing you did before in the LM, and you put family equals binomial. This is now a logistic regression. We're predicting the long wait based on the pub and waiting times, but we're going to use a binomial family or a Bernoulli distribution to make that prediction instead of a normal distribution. If we used the normal distribution, that's our linear probability model from above. Okay? Now, the logistic distribution is kind of more challenging to interpret. Since we're dealing with log odds, is this the distribution of the y or the x values, Sophia asks. The family argument describes the distribution of the y values. We never really adjust anything for the distribution of the x values because that's not as important statistically. It's just dealt with in terms of the expected values. But the y, we do need to figure out what distribution that is. So logistic regressions give their results in terms of what are called odds ratios. So like we were talking before, it's a linear regression on the log odds. These reflect changes or baselines in the log odds. So if we have a wait of 0 minutes in the Berkeley, our log odds is negative 2.251. Okay? Now, I can convert that back into a probability, but these predictions are non-linear in terms of the probabilities. So you read these as a unit change, waiting an additional minute means that I increase the log odds of it being a long wait by 1.9. Now, that effect is nonlinear, right? In terms of probability. It is linear in terms of the log odds. Fortunately, no human really thinks about things in terms of the log odds. Instead, we think about it in terms of probabilities, generally speaking. How much does this increase the chance that your wait's going to be too long? So the way that I suggest you work with logistic models is using the predict function we used before. In the earlier linear probability model, you can just get the probabilities straight from the coefficients. In this case, it's not as easy. That's because the model is nonlinear in terms of probabilities, but linear in terms of log odds. So to do that, I might say my scenario is that, let's say I'm in the Gallimalfrey both times. And my waiting time changes from being a wait of 4 minutes to being a wait of 5 minutes. So my scenario is a data frame with 2 rows. Then if I predict using the logistic regression and the scenario, I get back something I'm not going to like. By default, R's predictions are in terms of the units of Y. So these are the log odds of Y, the log odds of a wait being too long, in the Gallimaufry for 4 minutes and in the Gallimaufry for 5 minutes. Now, if I look at the estimate of the waiting time, which is about 2, I can see that these are linear there. In order for me to make predictions on the probability scale, I need to use a special argument. Type, and I think I document this in the workbook. When you're working with the logistic regression, you say type is equal to response. So what this means is that I want to get a prediction in terms of the response variable, y, not in terms of my transformed variable, which is the log odds of y. If I do this, I get my probabilities. So if I'm in Gallimaufry for 4 minutes, I have a 99% chance of it being too long of a wait. And if I'm there for 5 minutes, I have a 99.98% chance. So you see, those two probabilities are very similar. Now, the reason why this is confusing for some, let's say I want to do a whole bunch of predictions. So now I'm going to use the rep function that I talked about before, and I'm going to say the Gallimaufry, and I want to replicate that 10 times because I want 10 rows where the Gallimaufry is my pub. And for the waiting times, let's check out observations that go from 1 minute to 10 minutes. So now my scenario has 10 predictions, and my waiting time is 1 minute, then 2 minutes, then 3 minutes, then 4 minutes, then 5 minutes, and so on. Okay? If I make my prediction in terms of the log odds, I misspelled Gallimaufry. If I make my predictions in terms of the log odds, those are linear. And I can show you that. Qplot, scenario. Yes, you can, Anna. Yep, exactly. Good realization. I just want to get through this right now. So if I show you a plot of the waiting times that I'm making predictions on versus the log odds that I'm predicting, that's a straight line, as Noah said. On the y-axis are the log odds, and the x-axis is what we're regressing. It's a generalized linear model because that is linear in a transformed version of y. The log odds are not what we're dealing with at the start, but it's what we run the linear regression on. You transform it through the link function, which in this case is the logistic, and you get the linear regression. So you all see that this is a linear prediction. It's a line of best fit for the log odds. Now, if I put that in terms of the probabilities by saying, okay, I don't want log odds, instead I want the type of prediction that comes from my response variable, which is a probability, that's nonlinear. if I wait for basically just under 1 minute, about 1 minute in the Gallimaufry, my probability is 0.7. If I increase my waiting time by a single minute, my probability jumps from about 0.7 to over 0.9. The effect of an additional minute is way smaller. The change in probability is only, what, less than 0.05, maybe 0.04? Let's look at that over here numerically so that we can have it accompanying the plot. So you see we start off with waiting 1 minute, or waiting 0 minutes, I think, no, it's 1, is your probability is 0.69. Waiting 2 minutes, so the additional effect of a minute increases that probability to 0.94. Waiting another minute at that point only increases the probability by 0.05 to 0.99. So it's non-linear in terms of the probabilities, but it's linear in terms of the log odds. Does everybody see that? Because that's the big point about logistic regression. We're making linear predictions about the log odds in exactly the same way we are with the linear probability model. It's just a linear regression. But instead of doing the linear regression on the binary outcome, we're doing this transformation to get the logistic scores, to get these log odds. So the difference between these two is about 0.19. The difference between these two is about 0.19. The difference between these two is about 0.19. I think I can use the diff function to show you that. Each of the differences on the log odds is the same. Each of the differences for the probability scale is nonlinear. Starts off big, gets small as you get close to 1. Okay? So the way that I recommend that you interpret the linear regression or the logistic regression is using these types of predictions. So give me a predicted value at the mean, and then a predicted value at the mean plus 1, and you're perfect. If you do the reading in the Gelman, he offers you a suggestion on page 82. And this suggestion is called the divide by 4 rule. Okay? And I'm just going to run you over a quick example of that, and then we're done. So I'm going to put up the logistic curve here so you see the logistic curve. Whoops. Okay. So in this perfect theoretical example, beta is the biggest in terms of probability when we're right in the center of the curve. And beta is the smallest when we're up top, right, in terms of the probabilities. In the log odds, this is just a straight line, so the slope is constant always. Okay? So the rate of change in terms of the probability, which I'm sorry, I shouldn't have said beta. The rate of change in terms of the probability is large at the center and is small when you get close to 0 or 1. In terms of the log odds, it's constant. So it's always just going to be beta. And when you look at logistic, it just gives you that one number. That one number is the slope or the intercept of the line. So this would be the slope, and that would be the contrast of the line in terms of log odds. And as I show you down here, that results in nonlinear curves. Okay? So Gelman's rule of 4 on page 82 says, okay, a convenient approximation to give us a rough rule of thumb about the effects in a logistic regression, if I don't want to go through the hassle of making that predict for a scenario I can understand is look right at the center of the curve. I know that the change in probability is greatest there. And I know that when I get really extreme, the change in probability is just going to be 0 anyway. So at the most, the change in probability is this beta divided by 4. That's the maximum difference in your probability that y equals 1, corresponding to a difference in x, as he says. So I recommend that you make your predictions based off of doing those predict. So something like I did earlier, where I say predict myself a scenario and say, okay, the difference between waiting 1 minute and 2 minutes is 0.3. So so a 30 percentage point increase in the likelihood of being too long of a wait. But according to Gelman's rule of 4, I would say the maximum increase would be 0.957 divided by 4, which is about a 48% increase for every extra minute. So that is about the change in probability at the center of that line, going from 1 on the other side to 1 ahead. So that's just a rule of thumb. It lets you talk about the change in probabilities right there in the center of the curve. Using the predict function, you can get the change in probability wherever you want. Sophie asks, where did I get the 0.957 from? I got it from the logistic regression summary. So just like before, I can get a summary of a logistic regression. And that's going to be the same exact things as I talked about in the linear probability model, except for now, instead of probabilities, y is the log odds. So this is the change in the log odds. And using this rule of 4 from the Gelman and Hill book, you can get the largest expected change in probability. But as I just showed, that change in probability will change as x changes. So for really big values of x, the changes in probability are really minute. And for values of x around the center of the logistic curve, changes in x will result in large changes in probability. Again, that's because it's linear in the log odds. We just get one slope. But when we transform it back to probabilities, it becomes this S shape. And that's nonlinear, right? I'm increasing much faster here than I am up here. Hannah asks, why is it divided by 4? I would suggest that you read 82. Zoe says, was chapter for Gelman on the reading list? I don't think immediately, but it should be, or it should be the Introduction to Statistical Learning that is on the list. I can't quite remember which one. Both of them will have the necessary discussion, as I said before, but I'm just suggesting these alternatives as I have before. So let me pull up the reading list, because yeah, so the ISL 4.1 to 4.3 is going to have a lot of the good discussion, and then the Gelman chapter 5 is listed as an alternate reading. So I'm just giving you that kind of divide by 4 rule. Gelman's the only one who really talks about that. Other people don't suggest that. If you do want the alternate reading on logistic regression from Gelman, you can just check chapter 5.1 through 5.2. You don't really need the 5.3 and on. The suggested reading from this book on the machine learning perspective, if you find that easier, you'll get the same kinds of content we've been talking about before. Isabel asks, why do you want the largest expected change in probability? Well, good question. You don't necessarily, but what the argument is that you know that the smallest expected change in probability occurs up here when the function gets flat. And that's basically 0. So when I do the predictions in terms of the response, you see when the minutes are going from 9 to 10, my change is minuscule. From 8 to 9, from 7 to 8, those are really, really small. So we can always get the lower bound of the change in probability, and that's 0 when we're out in the tails. But some logistic functions change quickly, and some logistic functions change slowly. So you see here, this one changes pretty quick. And in fact, all of these functions change at the same rate because they just has one effect for weighting, which is like earlier when we had the 3 lines with different intercepts. Same kind of concept. This one crosses the y-axis there, that one crosses the y-axis there, and that one crosses the y-axis there. That's like the intercept. The rate of change, how quickly they go, is constant. And that's the same as when we were doing the linear probability model. But if I go up to the, here, I'll show you here. So I'm showing you the logistic curve for a specific logistic regression. So if I change the, I think it would be 2 star y, 2 star x divided by exp 2 star x plus 1, and we say qplot x equals x, y equals y2, geom equals line, color equals red. Let's see if that'll work. I'm not quite sure. Oh, line equals y2. So you see, okay, I'd like to have them both on the same. So I'll just do this. ggplot, sorry, data frame x equals x, y equals y, y2 equals y2, plus geom line as x equals x, y equals y, color equals black, plus geom line as x equals x, y equals y2, color equals red, plus ylab. Okay, let's try this so that you see what I'm talking about. So you see how the black curve has a slope of 1 on the logistic scale. So in terms of its log odds, it's just a slope of 1. So it's like 1 times x. So just to show you, the log odds for number 1 is just x. And then the log odds 2 is equal to 2 times x. So if I were to make a So if I were to change my outcome from being the logistic version to being the log odds, and say this is, instead of that, I'm going to say the ylab log odds y equals 1. So in terms of the log odds, these are just 2 lines. They have the same intercept, which is 0, but they have 2 different slopes. The red line is steeper than the black line. When I put this through the transform of the log odds, get these. So they have the same intercept, which means basically that their maximum occurs in the same place, but the speed at which they change is different. The red one is faster, it gets bigger faster than the black one. So it's linear in the log odds, and then we put it through this transformation and it becomes nonlinear in terms of the probabilities. A sharper slope in the log odds becomes a faster increase in terms of the logistic. So we always know that the smallest change in probability is 0 at the very tails. But the slope of this center region gives us a little bit of an indication about what to expect about the slope of the line. Obviously, around the curves, we might get quick changes in probability. So Isabel, the reason why we use the largest expected change in probability is because it's stable over that center range. It's just a good example, an easy way to make a prediction right in the center of that curve. It's like the flat part of the line. Okay? So again, I'm not going to ask you to deal with the mathematics of this. If you're interested in it, the Introduction to Statistical Learning and the Gelman Chapter 5 alternative reading should both have enough explanation and clear kind of discussion to make it obvious. And we're slightly ahead of the reading this week because of the way the course is designed. I wanted to lecture it first and then have you read. But the whole point is that these are just linear regressions on a transformed y. So I'll probably leave this in just because I want to make sure that you can see the two different ones. I'll make it cleaned up so that I'll say this one is a log odd slope of 2 and this one's a log odd slope of 1. Does anybody have any further questions? You should be able to do most of the assignment outside of the log odds if you're not comfortable yet and want to do the reading. And you still have about a week to get that done. But like I said, most of this code, as long as you can use the GLM and the predict functions, you're fine. You'll be going well. And all that stuff is documented in the workbook. Okay? So I'm going to call it here. And then my suggestion to you is that you finish the workbook through what I've talked about today and then move to the assignment. Or if you'd rather, just work on the reading. Okay? The assignment is due on the 5th. Yes. So you still have a week. So I'm going to stop screen sharing now. And then I'm going to stop recording now.